we have a lot of slides to go through. It's a small room. I know it's going to get a little bit hot, but if, as we go through, if you have a question, if you're confused about something, go ahead and fire away. Don't ask a long, complicated question, but if it's something for clarification, go for it. I'm sure there are other people that will have a similar question. How many people here are mobile developers? What are the rest of you? Back-end developers? Just really good guys? Okay, all right, well, thank you for coming. All right, so about me, I lately am focused on mobile security, specifically focused at API security and mobile attacks on APIs. I started out, it was a long road, started out as a chip designer way back in the day. Then I started working into sort of low-level hardware software interface, did a lot of reconfigurable computing where I sort of created hardware on the fly and traded hardware and software off. That was pretty wild. Got driven into the embedded space, kind of working my way up the software stack. That drove us into, as a company, doing some work on porting Android to kind of exotic type platforms, did some work on hardware security module acceleration, and that drove us into mobile security, the combination of Android and HSM development. So my job title, if I have one at Critical Blue, is called Growth Hacker, which means I get to do whatever I want as long as it results in increasing the revenue of the company. So I get to play and hack away, do a lot of demo work. I blog over on Medium or on our own internal blog. I do marketing studies occasionally. I do whatever it is to do it, and I'm really interested in the topic of mobile API. I do offer a product called Approve, which you can see at approve.io if you're interested. If you're really interested, just come and talk to me afterwards. So mobile attacks over the last couple of years have definitely been exploding. This data is from 2018, the beginning of 2018, and shows that of the sort of roughly 200 million attacks they looked at, 51, about a quarter of them were coming through the mobile attack surface going through. So it's growing. It still seems to be a little bit easier to attack through a web application kind of, or a plain HTTPS kind of attack. But mobile is definitely getting the majority of the transaction space now, and people are starting to look and see what they can exploit there. So APIs are always talked about as a new business opportunity. They also offer a lot of vulnerabilities. Public APIs, if you're using the API, it's usually very well documented, so you don't even have to reverse engineer it. You can start attacking by just starting to play with that API. Structured API styles like REST make it pretty easy to guess what you might try next. So if you can find a hook into one thing, you can start playing with different verbs and try gets and posts and various things to see. So you can kind of randomly explore most of these APIs. Leaky APIs will disclose implementation details not just when you guess right, but when you guess wrong too. A lot of times somebody will give you a lot of information about their backend in their error messages if they haven't cleaned them up and taken them out. And lastly, if you're not careful, if you're using a lot of automated tools to help specify your APIs and then auto-docking what you've got, you can accidentally expose a lot of API work. So you probably can't see it down here, but this is documenting how to shut down the whole backend system with an admin shutdown call here. So I have to give you one example at least of an API attack. This one was a couple years ago. It involved somebody's rear end. So there was an attack on Instagram, a really simple attack actually. All they basically did was from a system they controlled, they issued a password request, they captured that request, and they filled in a celebrity's name instead of their name and sent that on to Instagram, which then gave them back enough information that they were able to take over the account. Doesn't work anymore, but it's the kind of thing that it's very easy to accidentally expose what you're doing. Now, oftentimes we talk about just a single API, but in reality, there are many different apps firing to many different APIs. So you might not just have a native app in Android, you have an iOS app, there might be a React Native version, you might have something running in the browser accessing the same APIs. Every application probably is going to hit multiple APIs. There'll be one you use for user authentication. In this example, you might be trying to rent a car in a hotel, check the weather in the location you're trying to go to. All of these will potentially be different APIs. The APIs themselves will have many different versions potentially. The apps themselves will have many different versions. So there's many, many combinations here of attack surfaces that you can go after. So I'm going to use today an example called ShipFast. Think of this as kind of a courier service or a food delivery type service where you have a bunch of drivers who are going to pick up packages and courier them to the end destination. So it's an Android app here. The first thing that the shipper is going to do, or the driver, is going to go ahead and log into the application using a standard OAuth 2 type login. No issue there so far. And that will pull up a map. I should have told you my company is based in Edinburgh, Scotland. I'm based up in San Francisco. So we're international today, and we're actually looking in London. So you've got drivers in and around London looking for apps. They're going to indicate that they're available by clicking this button. And ShipFast will, knowing their location, tell them where the nearest delivery is that they're going to go get. So it's showing a pickup point here and a drop-off point here. The driver will accept this delivery, and then they will go collect the package and deliver the package. And they will get paid two ways. They will get paid for the actual driving itself, and also there's an optional gratuity that in this case, unfortunately, was £0, which for us Americans translates to $0. So they didn't, I'm good at math. So they didn't like that too much, but that was the nearest shipment. And ShipFast's motivation obviously is to maximize the throughput here. So they're interested in only giving their drivers the shortest path that they can get so they can maximize that throughput. So this is what the sequence of API calls would look like. It's a typical REST API. This is the interesting API call here. This is the one that gets the nearest shipment based on a latitude and longitude. So the app itself will give its positions and it will get back the nearest route information, which will then display. And the only protection it's using right now is a standard OAuth access token kind of thing. So one of the drivers was pretty good at hacking around, and he really wanted to go after more high gratuity shipments and not so much the ones that are nearby. So he created a prototype web app here that works with the existing app. And the first step that's required is the driver will go and log in. So he'll use the same OAuth 2, auth 0 endpoint in this case to log in. So if ShipFast thought that they had protected themselves by requiring their drivers to log in, the driver freely gave away those credentials because he thinks he's going to get something for that service. So OAuth, user authentication by itself, is not going to be good enough. So he logs in, and then he clicks show me all the shipments that are kind of around my space. And you can guess what it does. It repeatedly calls kind of for X equals this and for Y equals that. It calls that API call saying, show me all the nearest shipments everywhere I am around London in this case. Comes back with a list here, looks down the list and says, okay, this one here has a 26-pound gratuity. It's a little bit further, but I'm going for it. So they'll grab it right there, and it will, for the driver, accept that package. And then when the driver goes and logs in, it'll immediately show him his delivery there. So he's now spoofed the ShipFast system and is going for maximum profit in his case by getting that 26-pound gratuity. So I want to stress that user authentication is good, and we'll get back to it in a little bit, but it's not enough. It's really equally important to know what are you using? Can you trust this app? Is this app what you will allow to access this backend endpoint? So the first step that most people would take is they'll add an API key along with the API call. So this key is a secret or some combination of sort of public ID and secret that hopefully is kept safe inside the application so that when the application is ready to make an API call, it appends that in the headers typically. Not so much a good idea to put in a query string because those are easy to see, especially if you're looking through logging. And so it puts it in the header, sticks it through the backend. We'll check and see, does it have the right secret? If so, it will let it through. So you really need to protect that secret well. So here we've just added the API key along with the user token that's being used. So there's a few attack surfaces to look at. Is it possible to leak that API key secret through user credentials? It actually is if you're really bad at what you're doing. Is it possible that it's not very well defended on the device? Is it a constant in your code? Or is it stored somewhere in secure storage that really isn't that secure? Or can you somehow get to it during the runtime if, say, you have a rooted phone? When you send it across the wire to the backend API, is it possible to snoop that traffic and find that key? Remember, it's just this big, fat, static secret. So if you can find it once, then you found it and you win. And for ShipFast to take it and issue a new key requires kind of an upgrade of an app and a whole upgrade cycle that they really don't want to go through. And probably the best attack surface of all is accidental leakage. Did you just give away the secret by publishing it somewhere? So let's look at some basic mistakes. The first one is don't publish it to GitHub. We've all probably done that. This was actually mentioned in a talk yesterday. Ryan Hellier, a few years ago, was very careful about open sourcing his application and pushing up his stuff into Git. He got it all set, fired it away, and 4 hours later he had a big bill from Amazon. And he was certain that he had taken his WordPress configuration, which had his credentials, and not put it in. And he was right, he hadn't put that in, but he kind of did what I often did. He made a copy of that file as a backup while he was doing it instead of just pushing it back to the repo. So the saved backup file was actually in the GitHub repository. So he had all sorts of people hopping on this and taking those credentials and using it. So in ShipRaider's case, they needed to know that API key now to get back in business. And in this case, it's an Android app. And ShipFast was really not too sophisticated in Android apps. So what they did was they had actually put the API key in the manifest that ships with the Android code. So the manifest is very easy to see by just unzipping the APK, which is the package app. Come on in. Would you like to take over for me? Okay. All right. So Bing, they unzipped it, went and looked in the manifest. It's a plain text file, and here's that very messy looking key. So ShipRaider was back in business in no time. So it's going to happen. No matter how good you are, you're probably going to leak something or make a mistake somewhere along the way. So what's your backup plan? Typically, you're going to do exactly the same thing you do with web apps. You're going to be looking for some sort of abnormal behavior. Are people trying to probe your API to guess around? Is there a kind of high frequency rate there? Are they trying to DDoS you by making a lot of application calls? So not low-level DDoSing, but actually just making a lot of, the canonical one is to make a lot of search requests that require a database access to just fire away. It looks like real traffic, but it has some characteristics that maybe you can filter off. Are they just trying to scrape information if there's a lot of valuable information? If you're like a booking site, is there information that they can get on pricing there? Are they trying to attack you through credential stuffing? These are kind of behaviors, once you have the API keys, that hopefully you can detect. And traditionally we use something like rate limiting for these kind of deterministic kind of things with a leaky bucket kind of pattern. So if a request comes in at too high a frequency, the bucket is filling up while it's draining out at what you expect it to be a regular rate that it's accessed. And if it overflows, then you know you've got a problem. So variations on this. And in ShipFast's case, we're doing a trace across, in this case, all of London. So there is a burst of activity of this API call. So it may fill up this leaky bucket. AI, deep learning has come, so you can do behavioral kind of checks as well. Does this traffic characteristically look like bad traffic you've seen before? Can you learn from that? And in this case, just as a variation, if you see the same guy make a request here and there, behaviorally, you know he probably can't be in two places at once, and the velocity of his car would have to be too fast. So you could learn those kind of rules as you go through. So that's your backup plan. It's not perfect. It's a statistical game. You don't want to be telling people, sorry, we think that you're bad when you aren't. So a lot of times those kind of constraints are pretty loose. You don't want to lose valid business as a result, but they are what everybody uses to try and protect yourself once you've been breached or even as a normal operation. So one of the attack surfaces was secure communications. Can we just see the secret when it gets transmitted to the backend API? So everybody, including Google, tells you to move over to HTTPS or TLS, which will encrypt through a handshake back and forth. It'll encrypt all the traffic, so hopefully it can't be seen in that case. But you really need to trust that the backend certifications are legitimate. What will typically happen is you will break TLS with a man-in-the-middle attack, which you might think is reasonably hard, except remember that the attacker controls the device itself. So typically what an attacker will do, or what a man-in-the-middle proxy will do, will just simply install an invalid certificate on the device saying, trust anybody that chains back to this certificate. So since they control the device themselves, it's very easy to set up a man-in-the-middle attack here and break basic TLS. So what can you do on a mobile device? One approach typically used is called certificate pinning. So the attacker will control the device and is free to add certificates onto that device, but hopefully he won't control the app itself. So you can sort of create a whitelist of acceptable certificates within your application. And say, I will only accept TLS connections that come from this whitelisted set of certificates. Those certificates are a lot like secrets. So you've now added some more secrets into your app that you need to figure out how to protect. But they are definitely going to filter out all the traditional, easy man-in-the-middle type attacks. So.
These are WebKit-based applications?
No, this could be a native Android or iOS type application. Right. So it could be any hybrid type applications as well. It's just normal HTTPS, TLS kind of traffic, right? So in this case, ship fast countered by adding the certificate pinning, and ship radar countered back, and there's kind of a back and forth. And what will eventually come down to, and this is kind of a subtle point but an important one, is that the app itself is going to make a decision as to whether it trusts the environment or not. So there are a lot of runtime frameworks that are built up that try and intercept at that function call that's making that decision point. So in this case, there's a package called SSL Trust Killer, which will actually try and intercept the call of, do I trust this? And it will kill that and say, of course you do. And so it will hook it and pull it out. So there are runtime checks, we'll come back to that a little bit later as well, that you need to defend against. So it's not just a static secret on the device, it's what's happening while the device is running. Pinning's also kind of not that well adopted because it's kind of a pain to maintain. So you've got these server certificates, people like to rotate them, and it's kind of a maintenance headache to put new certificates into your device or not. And you are depending on the app integrity to prevent an attacker from putting in any kind of bypassing hooks and frameworks to get through. So another approach, which Ship Fast will try, is can we get the secret out of the channel altogether, but still have the effectiveness of the secret itself? So as the next step, what they actually did was they took the API call up here. Let me see if I can use this. It's probably hard to see, but they took the API call right here to shipments active and the OAuth authorization token, and they concatenated those together. And rather than just sending the API key along with it, they actually used that and hashed it with the secret to come up with a signature. So they took that signature, and that signature is what they actually sent in a header. So you still have your OAuth authorization token here, you have your normal get call, and then you have the signature here. So you can see, instead of sending the secret, what they sent was a hash of some entropy, some random-ish kind of information. In this case, was the API call and the OAuth token, and hashed that across. And then at the back end knows the secret and will actually perform that same HMAC calculation right here and compare, did I get the same answer? So at no time was the secret itself actually on the wire, simply a somewhat semi-randomized hash of that secret as we went through. So that's a big step forward, because now, even if you do break through in TLS, you're not going to see the actual secret. And it's reasonably, well, you may be able to do a replay attack through this, because it's the same API call. And if you have a long-lived authorization token, then you could successfully replay it. So you may want to add a little more entropy into a call. But this was ShipFast's first try, and let's see what happened.
This only works for private APIs, though, right? Not a public API.
Yes, unless the public API was somehow issuing a secret out inside the app. They're welcome to put a secret into the app, but if it's a popular public API, then that secret is sitting on the device, right? So you certainly could use it for a public API, but it might not be as easy to go. Okay, so it didn't actually take ShipRaider too long to break the HMAC. That was a big step forward because we reduced the attack surface on the communication part. But they simply went and they got a hold of the APK, the Android package. They unzipped it. They used some reverse engineering tools. And even though the code may have been somewhat obfuscated, that secret's pretty obvious sitting there in the device. It's a string constant with a lot of randomness looking to it. So they very quickly found what that secret was. So the bottom line is, no matter how hard you try and hide a secret, if it's valuable enough, people will work as hard as they can to figure out what that secret is. So it didn't take them very long to go. ShipFast needs to respond. What might they do? They can start to try and hide the secret a little better. So they might break it up into multiple pieces and somehow combine them in some way. So they wrote here a for loop that does a lot of exclusive ORing of pieces of the secret. So now, instead of having the secret stored in one place as a long string, now it's stored in little pieces in various potential places around your code. So that's a little bit better, but not that much better. You're still having to do a little work. Yes, sir?
Just a curiosity, you just didn't want to use the legal department and just file a lawsuit. I mean, this is fun, don't get me wrong. Was there also a legal approach, or this is very good for me.
So that's really an interesting question. So I don't usually talk about the legal side. The guy before me talked about insurance, so I guess he's opened the door to these kind of non-technical things. We do have customers who are constantly being attacked, and they certainly do the legal channel as well. Depending on where the attacking is coming from, that is more or less successful.
Because the shipper API also probably, the company, the rating company probably comes from a very specific set of IPs. So you could basically block them up, not like keep rotating them. But you can, there's a way to maybe pick up the traffic type. Or,
yes.
And try to say, hey, is this instead of you working on defending, working on recognizing when it's them that's actually attacking and just blocking them out.
Yes,
right?
that's certainly possible, and that's very much the approach you would use with any kind of generic web traffic.
Yeah.
Right? So all those options are still on the table. I'm just trying to focus on the mobile side of it. All right. So the bottom line on this one is that you can't generate a random secret here and use it. The secret needs to be known by both you and the endpoint. So therefore, whatever calculation you do has to be repeatable. It has to be deterministic. So that makes it breakable eventually. So ShipRaider can steal this. If the computation gets too hard and they just can't get that, then they might actually run it, repackage the app into a debugger, and walk through until the debugger is just ready to send it away, and they can grab the computed secret right there. Again, it's deterministic, so if they can grab it after it's been computed, it's just as good to use. It's not going to change over time. So ShipFast is going to have to counter again with more app integrity runtime protection. Can we detect that the debugger is in the space and refuse to allow that debugger to do anything useful? And there are techniques to do that type of stuff. And it's kind of a cat and mouse game.
This is making development get rather expensive.
Yeah, if you're denying your developers debugging, but
No, I mean just this whole process is.
no, because after you've come to my talk, you're going to know the right way to do things, and you come to the shortcut, right? Sorry. Okay, but yeah, you do. There is a fair amount of subtlety to all this stuff as you go through, right? So, I'm really going to mess up here. Okay, so. You can try all sorts of app hardening techniques. Obviously, most applications will have some level of obfuscation tools that are going there, changing the variable names and things. But there still is structure that can be detected. There are advanced obfuscation that try and change the code flow and throw in a lot of false traps and things. So it's a game. But if the secret's valuable enough, it will be grabbed somehow. You can add anti-tamper type code to your code to try and say, gee, it looks like this code's been tampered, I'm going to shut down. Again, those anti-tampers are decisions that are being made in the application itself, so they're vulnerable to hooking kind of attacks. So there's definitely a back and forth kind of game. The extension of that sort of custom for loop that we put in first, if you keep going, you can, rather than hide a secret, you try and hide a function inside the device. So there's a scheme called white box cryptography where you're trying to create a custom function for your secret. So it's a piece of functionality that you drop into the app. Again, there's a decision being made, so you might be able to hook it at the right point. And then you can try storing stuff in software key stores or hardware key stores. These are more or less secure, depending on what you're doing, how rooted the device is. And the hardware-backed key stores tend to be a little bit harder to use. So we don't see as many people using those kind of things. But there you have ultimately some certificate secret kind of thing embedded into the hardware itself. Okay, so let's flip back to user authentication just to go through it. ShipFast and everybody else pretty much uses OAuth 2 in the mobile space. And I want to stress to you today that you might think of it as an authentication protocol. You're authenticating a user. It's really designed to be an authorization protocol. And I actually think it's authorizing the application to access the resources. It's definitely about authenticating the user so that you can authorize the app to go through. It's often extended with OpenID Connect, OIDC, which does have a more formulaic way of doing the user authentication portion. There are many different grant types in the mobile space. The standard grant flow is called the OAuth 2 code grant flow, and we'll go through that. When an OAuth 2 client is going to actually make a request, it's broken down into the client itself, the resource owner who is going to authorize the app to go through. That's typically the guy that's pushing the buttons. You might think of him as the user, but they call it a resource owner. There's an authorization server that's going to be granting the authorization to go through. And then there's the resource server itself, which holds the resources that are trying to be accessed. So you might not be able to follow this too closely, but this is the OAuth 2 code grant flow. The important thing to notice here is there's a front-end piece and a back-end piece when we go through. So your app itself, when it's ready to go, the app is the client in this case, it will initiate an authorization. And rather than just asking the user to type in his password, what it actually does is it directs over to the user agent, which would typically be the browser sitting on the device. And it says, it delegates essentially the gathering of those credentials to that user agent, which is the one that actually interacts with the user. And the user enters some credentials and says, yes, I will grant certain authorization to this application. And those credentials are submitted back to the backend authorization server, which uses them somehow to authenticate the user. So maybe it knows how to look up the password associated with that user. And then it returns an authorization code, not again to the client, but back to the user agent. And it's the user agent that then is redirected this code back to the client. So the important thing to notice here is that the credentials themselves are never exposed to the client. The client, if it's successful, gets back an authorization code, which it, on its backend flow, it takes that code and some sort of client secret that is known only to the authorization server and sends it up. And if that code is valid for this client app, then it returns an access token, which is a JWT, a JSON Web Token, that has been signed and has a limited lifetime. The lifetime itself depends on what kind of app it is. If it's a very highly secure app, the lifetime might be quite short. A banking app maybe has a 30-minute lifetime, let's say. If it's a gaming app, the expiration time might be 6 months in the future. Every time it expires, potentially the user will have to relog in. So they don't like to interrupt your gameplay to relog in periodically. But obviously a bank will not want credentials that are sitting there for longer than a single session as you go through. And the important thing to notice about this backend and front end is that, as I said before, the client never saw their credentials, and the user agent, the browser, never actually saw the real token that is stored on this device. Because you could be snooping in this browser space, and you don't want that token to be visible. So that's why this strict separation is undertaken here. Once you get that, then when you make an API call, you simply add that token along with the API call. It's validated, and if it's not expired and it's properly signed with the shared secret, then you're good to go. Now there is an OAuth 2 refresh thing. So in addition to getting a access token, you will also get one or more refresh tokens. So you can employ a strategy where the token itself may expire. When it expires, if you have a refresh token, you send that back to the authorization server with your client secret, and you get back a fresh access token. And the policy is a little bit loose on how this is employed, but typically you would like these refresh tokens to be kind of single use only, where you use it and then it can't be reused in case somebody again can snoop on this transaction. So one of the things that happens on these kind of devices, there are places where things can be intercepted. So on mobile devices, there's something called Proof of Key Code Exchange, or PKCE, that's added to this flow. And here, when the client initiates the initial request, they will randomly generate a random value, and they will hash that random value and send it as a code challenge through the user agent. It wanders through, and it's stored here in the authorization server during that front end phase. Then when it wanders through and the client itself requests the token secret, it provides the unhashed value at this point, which the authorization server will hash and compare to the expected code verification. So it's able to verify that this entire chain has gone through successfully and gets that back. So there's this random secret, which can be a little bit hard to get your head around sometimes, but there is a case where we're actually generating a secret on the fly and passing it up to the authorization server, which saves it on the front end and then uses it again on the back end. Yes?
Is that the same as like the state parameter?
No, that's a different variation. Similar flow, but I honestly can't remember exactly why the state one was there, but anybody else know about the state? CSRF, right. Okay, great, thanks. Okay, so can we further reduce the surface of the attack? So the fewer secrets, the better is going to be our mantra here. So remember at the beginning I said there were multiple APIs. It would be really good if the app didn't have to have a key for each one of these different API services. So that really begs for just adding some sort of proxy in here. so that the app itself will only communicate with the proxy and therefore only have to use one key. So that's a key you really, really need to protect now because it's the key to the kingdom here that will then be proxied out to the proxy will know the keys, and the proxy is more secure than the mobile device is. So this is a good trade-off. So now we're down to hopefully just one key that we're going to be protecting. All right, so now I'm going to do the classic computer science magic of indirection. So we don't like secrets on the app, so what if we just said, let's just get rid of secrets. No secret on the app. And it's the 2019, so we need a SaaS service. So we're going to have a secret as a service right here, and when the app wants a secret, it's going to say, give me the secret, and the secret service will give it the secret, which it can then send to the back end. So we've now gotten the secret successfully off the device. What we haven't done is specified who can actually get that secret. So it might be a valid app, but the attacker could similarly request a secret from the secret service. So we haven't solved the problem yet, but we've at least gotten the secret off the device. And when we did the hashing as we went through, remember that we didn't send the secret itself across the wire. We actually computed some hash of that value. So let's kind of take the learnings from that as well. And this secret service is gonna issue JWT tokens instead. So they're gonna be signed by a secret that's known between this backend server and the service. And they're gonna have an expiration time, just like OAuth 2 tokens. So the secret itself is not actually gonna be delivered, but a token that will stand in for the secret will be delivered. And unlike OAuth 2, where there's a human in the loop, there's no human in this loop. So let's make that time to life, these tokens, let's make them really short, right? A minute, 5 minutes, maybe even less. So that if they are somehow observed, at least they have a limited, very short lifetime, and you don't need to wait for some user to key in some credentials here. So we still haven't solved the problem of what is a legitimate app, but at least we've now gotten the secret off the app. So we need some way of checking that the app is who it says it is. And so we're going to rely on some sort of authorization function. And the way this will typically be done is the app will ask to be attested by the app authentication service, our secret as a service. And the app auth service will challenge this app and essentially extract the DNA of the app. It will check and make sure that the code has not been tampered with at all. It'll have a bunch of checks to make sure that the code is tamper-free, that it will be randomized, these checks, so that it can't be replayed, and it will go through. So what that requires is that we need some sort of library sitting on the app that is going to fire that request up to the app auth service, and then the service is going to challenge it, and if it believes that it's the real app, then we'll issue a token. So you can push back and say, well, what's the difference between just having a static secret on the app and this challenge type service doing the attestation? It is possible to reverse engineer that drop-in thing, but it's going to be really hard. It may be possible to get access to that communication, but it's going to be really hard because we have a pretty tightly small defined problem that we're going after here. And probably the biggest difference that's going on here is that the app itself is no longer deciding at any point whether it is a valid app or not. The authorization service is making that decision. So there's no more obvious hook point where you can hook into the app and say, aha, you're telling me you're a valid app, I'm going to hook that and grab it there. Instead, the app auth service is delivering a token to the app. The app doesn't know the secret. It has no idea whether this token is valid, or if the app is not answered correctly, it may be getting a phony token. It has no information there. It's not involved in the decision there, and it will take that token and it will pass it on to the back end, and that's the best it can do. Yes?
Sorry, I'm kind of confused. So when you say secret, someone could put a proxy, you talk about that right there. I mean, a man in line can see the conversation, right? So therefore, if I can see the conversation, what tells me that I can't reverse engineer the app fingerprinting?
So which, are you talking about this one here?
Yes.
Yes. So what you can observe potentially there is the token. Only the token.
I think he was talking about the app off service, right?
Yes.
You're getting data from the app. Or
This one here,
Data, so
right.
I should be able to reverse engineer that data stream. So because the way you figure
Right.
the
So
app
you
is the same
can
way of
so
the
you
app.
can grab this. So no, there's going to be some randomization from this auth server. So it's going to fire, let's say, a nonce down to this guy, and it will randomize the responses. So the responses from the app will not be the same. They will be salted by this random value it's coming
Right,
down.
but if I know the 10 things that it's checking and then it's randomizing those, I can just change those 10 things. There's plenty of.
Sure. So if you are only going to do a limited 10 type check and you were not going to have coverage, then that would be true. So there's a science to this, just like there's a science to everything else.
Okay.
Actually,
Right.
I don't have to change anything. I just wait for the token to get back to me and use that.
That's right. You could, if you can spoof this channel, or if you can observe this channel, then you can grab that token. And you can use it for just a short period of time. But you could still set up a regular
I'm
routine.
assuming that this company that's
Right.
stealing your stuff might be also a client at the same time. That's how they keep stealing the stuff and being in front of you, right? They could be a client as well as the company providing the additional service.
Right, but there's a lot of randomization going on
Oh,
here,
okay.
right? So that wouldn't that kind of obvious stuff wouldn't work. But you do have to lock down this channel. So just a sec. So one interesting way to lock down this channel is to say, let's use triangulation here. So this app wants to trust the certificate that's here, but I've got somebody sitting here who's trying to spoof them, and they've put a bad cert on my app, let's say, so they're trying to get through. Well, when they make the request up here, this guy will go and check the cert from here. And this is in the cloud somewhere, right? And if this cert doesn't match the cert that's been presented to the app going in this direction, then you sort of have this dynamic pinning type approach where the certificates don't match, so something's going on.
What about like adding TLS binding to those channels?
You would definitely want to be running TLS binding on that. You want to lock. You want to do everything you can to lock down these channels. So for sure, you would do that. Yeah.
In OAuth in general, is there a disadvantage to having the authentication service be just another endpoint on the server serving up the private resources?
It would probably be considered best practice to keep it sort of isolated from them. And if you're using a third-party service, then it's likely going to not be co-located, right? But in theory, I'm not a deep OAuth expert, but I wouldn't think it would be necessarily impossible to do that.
So your application, this application would rely on multiple services. And you mentioned before that you would have to put those services to a gateway of some kind, right? Because
Right.
that way you can protect them all with one individual, with that one, correct? Okay.
Yep, so it would look like this. So in this case, your main traffic is still going through the middle. You would be going to an OAuth 2 service to do your authorization, and you would be going to an AppOS service to try and get a secret which is better protected, short lifetime, never actually on the device itself.
All that extra overhead is only being handled at the API server level. The other services, the API 11, 12,
Back
those
here.
guys can be lighter and don't need all that stuff because you're already doing it at the API server that's sitting in front, right?
That's right, yeah. So once you're through the proxy or your ingress service, then you're okay. But the important point is neither the OAuth 2 user service nor the app authentication service are in line with your API calls, right? Okay, so let's see where we're going. Okay, so now we have the ability to sort of get a secret on the fly that has a limited but finite lifetime. And so we now can take OAuth 2, and previously where there was a client secret required, we can now take this kind of temporary secret and throw that in place. Again, using a proxy pattern where we have this token coming through, and it would be validated by this adapter or proxy that would then issue the client secret to the actual third-party authorization service if you wanted. You could collapse this in if you had control of that authorization server, but if it's an Auth0 or a Google or some other provider, then you would want to stick an adapter in the middle. So this is protecting, again, the leaky secret potential that you can spoof off of the OAuth 2. So we don't have any secrets in the app. We are relying on secure communication, and we're requiring runtime defenses, as always. But at the moment, we've kind of locked the ShipRaider guys out as a result. So this is what the architecture looks like. The important point to realize is no matter what approach you're using, it's not just about the who, the user, it's also about the what. Can you trust what is doing the call, the application that's doing the call? Try where you can not to use a secret directly, but use some stand-in, whether it's a hash or whether it's a token with some time-limited value. In the case of pulling the secrets off the device, it did add another round trip to go get that, but now the secret's not on the device. So if you did want to change out your secret, you no longer have to take the million devices you have in the field and somehow upgrade them. You just upgrade it in the authorization server itself. The API server on the front end can be a pretty normal server. It's going to immediately filter out the tokens that don't match, either the OAuth 2 tokens or the AppAuth tokens if they're not properly signed. And then it can do all that kind of behavioral analysis stuff as well in the flow. So are we done? I don't know. It's always a cat and mouse game. We've made it a lot harder to try and capture things, but there's always going to be people trying to get through. So I think I've emphasized it enough. The identity of your application, the authenticity of your application is important as the user is. Try and limit all these attack surfaces. Maybe when I come back next time, we'll have a new set of attacks for ShipRaider to go through. And I'll post these things up, but there are some references here if you want to grab ShipFast. It's all open source code, so you can walk through that. I've blogged a bit about mobile API security if I went too fast in any points. Yes? So I would always recommend that you keep those controls in place. I'm just advocating that you try a little bit more sophisticated protection of the secret by moving secrets off the device wherever possible and using time-limited versions of those secrets that are not exposed publicly. But I don't think you can avoid the behavioral techniques and everything. The difference between the signature type approaches we're using here is you get a strong positive answer. Yes, this is a valid token, or no, it's not. With a behavioral type approach, you're going to get well, there's a chance that this is good, and there's a real chance that this is bad, and it's a statistical call, so therefore you're opened up to a lot of false positives potentially. So if you're a vendor trying to sell stuff, you typically go, no, I'm going to let the traffic through anyway. Or, yeah, the phone's rooted, but I really want them to buy the latest blah, 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 so I'm just going to risk it. But if you're a bank, you're going to try and lock things down even tighter. Yes? Yeah, so typically when you see words like nonce and salted, they're talking about that kind of stuff. So I would search around those terms. If you want a good walkthrough of OAuth 2, there's a book by Justin Richer and Antonio Sanzo, which I think is a pretty approachable book to go through. You're going to have to go through it multiple times because it's a pretty crazy spec to go through. Yeah. Yeah, those are behavioral techniques. In the case of Elastic Beam, it's definitely a deep learning AI kind of approach. And most of the API management companies will offer some of those type of services, right? Like Apogee or MuleSoft.
Still the kind of same comment about behavioral approaches or.
I think the fact that it's a statistical game means it's going to make some bad decisions occasionally. The more learning it does, hopefully the better it gets. And at some point, it's the only game in town, right? If they've beaten everything else, then the only thing you can look at is, does this traffic smell right or not? And that's what they're trying to do. So you got to have those at some point. Okay. Any other questions? So in the case of the OAuth tokens, it's easy for me to stand up here and say, yes, you should scope them as fine-grained as you can. That may get a little bit tedious at times, and so you need to make your decisions accordingly. But obviously, the least privileged kind of approaches is what you want to do. So there's a trade-off there, but be as specific as possible. Yes, a whole lot of great stuff you could do, and just in addition to just being a pass-through proxy, you can put all your behavioral stuff there. You can filter out bad tokens and kill the DDoS right at that point. You can adapt APIs. So if you've got an API coming and hits the gateway, it then needs to be maybe not just proxied on, but maybe you want to end up making a sequence of calls based on that API call to different backend services, right? So you can adapt things there. If it's a GraphQL server, that's kind of that taken to extreme in a sense, right? So yeah, API gateways are definitely worth spending time understanding and taking advantage of if you're running any kind of reasonable traffic volume. Nobody wants lunch, huh? One more question? No more questions? One more question. Right. So I haven't looked down in great detail, but what we're talking about here is the OAuth token that I used was called a bearer token. And that token is as good as cash. All right, if you've got it, you can spend it. So what you'd really like to do is get some identity into that token so that the token can be used by you and only you. So these new drafts are going in that kind of direction, and with the bidirectional TLS and the binding, and you mentioned the binding, that's all directions we're going in, and that will strengthen that OAuth flow. No, in general, I can say that things like whitelisting, they're a list of secrets or of things that need to be trusted and need to be protected, and they typically turn out to be a maintenance problem. So I've tended to veer off on those. Our big question was, how much could we push this indirection thing? Can we get the secret truly off the device and replace it with some sort of attestation that uses all the entropy of the application itself to make that decision? And can we do that in a high performance way? And that would get into kind of what I don't want to sell you right now. Well, I do want to sell you, but I don't want to talk about it right now. Okay, any other questions? Wouldn't you like to go to lunch? Okay, great. Thanks, guys.